We will start our lesson now. So it is about interpolation. So what is interpolation? Interpolation is a technique that we use to fit points that we collect, let's say, from experimental study. And we use that to estimate the value of the function that we will estimate between these 2 points or between these points. So if you want to calculate the function between these points, we use interpolation. Now, if I want to calculate the function outside these points, we use something called extrapolation. But here we only talk about interpolation. Now, what is the difference between interpolation and regression? So in regression, as you have seen that, we assume first that the data has certain error, randomness, uncertainty. So our target is not to go through the points. Instead, we are trying to find a line, a function, polynomial, etc., that minimizes the error between the line and those points. The line may not pass through any of the points, just between them. Okay? The target is not to have the line going through the points. On the other hand, in interpolation, we try to find the line that goes through each single point. So that's the basic difference. Now, you might ask me, okay, why? Why we need to have the interpolation, or when we have to use the interpolation in practical situation, and when we have to use the regression. In a very simple language, if your system that you are measuring that has a lot of noise, or your measuring device has a lot of uncertainty, then you know that your data points are scattered because of the impact of the noise. For this, you have to use regression. However, if you have a very precision device, and you know that this is calibrated, and you minimize all sources of noise, you are working under extremely controlled conditions, so you know that the uncertainty in the points are almost nil. Then you can, for this, you need to use interpolation. Okay? I don't know, for some reason I feel that the sound is not good. Guys, can you please someone confirm to me in the chat if you can hear me clearly or not? Okay, thank you very much. Okay, now let's move on. Okay, so if you want to draw this or show this visually, look here to the regression example. The points are scattered, and I have here a linear model that goes through some of the points, touch them, some of the points they don't touch them, so it goes something like this. On the other hand, in interpolation, again, as in regression, if you remember, we have linear and nonlinear functions. Same thing for the interpolation. But here you see that the function is not uniformly defined from the beginning to the end. Let me explain this, what I mean by this. So if you look here in regression, the function that defined the line from the starting A to the end B is clear is the same function. This is what we have. Okay? But here you see that different function exists, let's say between A, B, C, D, and E. You have a function different than this, different than this, different than that. So we have here 1, 2, 3, 4 different linear functions to approximate the interpolation, and all of them go. So I will have a function between A and B, a function between B and C, C and D, D and E. So we assume that the function is changing between the points. When it comes to here, you can see here, this is like a one function between point 1, 2, 3, so that you have like here one curve, and then another curve. So we have like 2 curves here. Now, a question asked is, can we consider this as an overfit? Is interpolation is an overfit? Now, overfitting is a big concept in machine learning. that when you try to enforce your function over the whole range of points. But here, if you look here, I'm having different functions between A and B. I don't have a function that fits all the points. Now, if I try, and I will show you in the next slide an example of overfitting. When I try to have a function that goes through all of them, then that will block an overfitting, and you can see the flaws for that clearly, as we will see in the coming slide. So, for example, here I will have 11 points. Now, if I have an 11 points, or if I have an n points, I always need an n-1 order polynomial to fit these points. Okay, so if I want to have a function that fits the whole thing, the 11 points, then I will need a polynomial in the 10th order, meaning a0 plus a1x plus a2x squared until plus a3x to the power of 10, so 10th order polynomial. Okay, so this becomes a to the power 10. Okay, so now this polynomial can fit through all the points, as you can see here. Now, if you look here carefully, now between 0 and 0.1, the function may be just like this. It may not be going up like this, but this is the price you have to pay when you use an overfitting. This is clearly is an overfitting, and may not be the wise idea to have an interpolation for the whole thing, because sometimes your system behaves differently at different ranges. So maybe the system from 0 to let's say 0.5 behave in a different way than between 0.5 and 1, or maybe from 0 to 0.1 behave differently than to 0.4. So then you have to have a local function for each region, instead of having one general function that describes the whole system, as we will see. So here, this is a much better approach of fitting the previous points. Instead of having one function that gives me some overshoot here, some overshoot there, which may not reflect the physical phenomena, it's better to have, let's say here, this is a linear interpolation. So between every 2 points, we call it piecewise linear functions that are different. So if I want to come and assume or estimate the point, for example, if this is, let's say, A and this is B, and I want to calculate something between A and B, something here, so having a linear function, maybe this or this depends where is the point you are interested in. This is the right estimate. But if you use a very high order, the function goes like this to fit all the points, and then you might have an unnecessary overshoot. So that could be a better way. Or you could have a higher order, let's say a quadratic, where you have every 3 points, you assume that they belong to the same curve. So point A, B, and C, one curve, C, D, and E. So you see here, this is like smoother than this one. This is more like a straight line. So this is a little bit of curvature here, you can see here. But you see, you can notice that between these points, there is sort of discontinuity. There is an abrupt change. It's not a smooth change. And that is the price you have to pay, because if you want to have a smooth change, then you have to go on a higher order, and then you will go to the problem of overfitting. So there is always a price or a compromise between an overfitting model to make the transition very smooth between the points, and to avoid the overfitting by increasing the order of the function. Now, how to find these functions? We have 2 approaches. Today we'll talk about the direct approach. Tomorrow we'll talk about the Newton divided difference method, and we will see the difference between the two. It's very interesting. This guy, we see him everywhere, and he dropped the apple in his head, and we keep on seeing him in many things. If he ate the apple, maybe not we have all this trouble. Just kidding. Okay, let's move on. So let's talk about the direct method. Okay. If n plus 1 data points, we have an n plus 1 data points. So we have from x0 to x of n. Okay. Are supplied, then we can use the interpolating polynomial has less the degree or equal than n. So the maximum degree I can have is n. That's the maximum. If I have an n plus 1, I can have up to n degree polynomial. Okay, so I can have, so this is the polynomial that I have. So start from a0 until x of n. So this is the degree that I can have, but I will have 11 unknowns. These are my constants. This is what I want to find. Okay, so I will have 11 unknowns. So you guess that you will need an 11 equation to solve for these 11 unknowns. If it is 11, or I need an n plus 1 equation, so that I can find this n plus 1 constant, which starts from a0 to an to an. Okay, so I could have a linear interpolation, so between these 2 points. So if I want to estimate anything, so this model is only valid between x0 and x1. Now I might have an x2 somewhere and y2. That model is not. So I have to give a range that this model is applicable to only this range. So if I want to estimate anything in this range, I will use this model. If I want to estimate something outside this, then I have to use another model that I will build myself as well. I could have a quadratic interpolation. So here, second order. So how many points I will need? I will need 1, 2, 3 points. Linear, bar of 1, I need 2 points. This is the minimum I can have. Cubic, then I have, this is a third, so I need 4 points. 1, 2, 3, 4. 4 points, and I need to have to the x cube. Okay. So the best way to proceed with this is to have an example. Okay. So we'll go through the example, and the example will require solving a set of linear equations. Okay. So I will be solving these in detail. So that if you have in the quiz, you know how to approach them. If you remember, even in the previous quiz, we needed to use Gauss elimination. Same thing here. We will need also to use Gaussian elimination. You have to use Gauss elimination. I was asked by a student, can I use in the quiz matrix inverse, for example? No, you cannot using MATLAB. You cannot. You have to solve them. It's like an exam. So in exam, you cannot use the computer to solve the problems. Of course, you can use the computer to verify your answer. I cannot watch you on that, but when you solve in the paper or in the quiz, you have to use the full answer. This is why in this example, although the answer here are just given to you without giving the details, I will solve the example with you in detail so that you can have this as a reference to refresh your memory again and again about the importance of using the Gauss elimination. So here we have an upward velocity of a rocket, okay, that is given as a function of time as such. So here we start from t0. The velocity was 0. This is in millimeter per second. Then after 10 seconds, this is the velocity. After 15 seconds, this is the velocity, and so on and so forth. Okay. And when we draw this, this is the x-axis, the independent variable, which is the time. And we start from 0. And the y-axis is my dependent variable, which is the speed. The question is, I want to find the velocity at 16 seconds, somewhere here. At t equal to 16, v is equal to what? So this is my question. Okay. So it is between now 15 and 20. This is the point that I'd like to use. So we will use to achieve this linear interpolation, quadratic interpolation, and cubic interpolation. Okay, this is the only way I will be asking you. So just to give you one example, you don't need to give more examples to understand this. Okay, it's the same approach. You have the points, then I will ask you to find for me the interpolation to solve the dependent value at certain independent number, that doesn't exist in the set of points, then you have to find the function. Okay, so we want to use a linear interpolation. Now here for the linear interpolation, I will need only 2 points. Okay, so I need to find the function between 2 points. The question is which 2 points? Obviously, I will select these 2 points. Why these 2 points? Because the 16 is between 15 and 20. I cannot go and find the interpolation between, let's say, 22.5 and 30, because this is only govern the relation between in this range. So it's between 22.5 and 30, only in this range. I am not interested in this range. I'm interested between 20 and 15. This is my range. Why? Because I want to find at 16. Okay, so I will take these 2 points and I will find the function here. So I will use a linear model. So your v of t is equal to this. Remember, this is only at the point of interest. Okay, so I know v at 15 from where? From the data. I know v of 15 is equal to this. So v of 15, which is t equal to 15, equal to a0 plus a1 times 15. I just substitute here. And I know that the velocity at this is equal to 362.78. Okay, and I know v at 20 at the same time, which is also a0 plus a1 times 20, which is equal to 517.35. Okay, guess what? Okay, that's what I wanted. What I want 2 equations to solve with 2 unknowns, which is a0 and a1. Once I know a0 and a1, I will come here and I will substitute. So it is a simple problem here. So I will subtract these 2. Let me subtract here these 2. When I subtract, you will have 5 a1 equal to 154.57. So your a1 is as simple as 30.914. So this is your a1. Now a0, just substitute in any of these 2 equations. So your a0 becomes 362.78 minus 15 times a1, which is 30.914. And this gives me minus 100.93. So from this, I can find my v of t, which is equal to minus 100.93 a0 plus a1, which is 30.914 t. Okay, so that is but this is defined. You have to specify. This is defined between these 2 points, 20 and 15. Only true in this range, not outside, not higher or lower than this. Now let's come to my question. I want to find v of 16. I will just substitute and will find this is equal to 393.7 meters per second. My problem is done for the linear interpolation. Let me check here the question. So we don't absolutely need to use guess elimination to solve. No, Gauss. Sorry, I mean Gauss elimination. No, we don't. We don't need to use Gauss. Here we are using linear equations. Okay, Gauss. Here we don't use. Sorry, here we don't need to use Gauss elimination because we have 2 variables only. There is no point. Okay, but once the system becomes more complicated, 3 equations, 4 equations, then we will need to use Gauss elimination as we will. Okay, now we'll go the quadratic interpolation. Okay, now again, I want to find v. Remember the objective: find v of at 16. Now let's go back here to the data. Okay. Now I need to add a 3rd point. The question is, should I add this point or add this point? First of all, why we need to add a 3rd point? Because to get a 2nd order polynomial, it has to be an n minus 1 2nd order polynomial. Then the number of points has to be the degree of the polynomial plus 1. Okay, so n if the degree of the polynomial is n, then I need n plus 1 point. Okay? Or if the number of points is n, then the degree I can reach to is n minus 1. So always there is a difference of 1 between the number of points and the degree of the polynomial. Always the number of points is higher than the degree of the polynomial by 1. Okay? So then I have to add either the 10 or the 22.5. This is the question. Now, how we decide? We see which point is closer to 16. Okay, so 16 is here. The difference between 16 and 10 is 6. 16 and 22.5 is 6.5. So 10 is closer, so I will take the 10. Now you might ask, what if both points are the same? Then you have the right to select any of them. It will not make a difference. Okay, so let's come here. So now I will have 3 points. The first one is V at 10. Okay, so it's A0 plus A1 times 10 plus A2 times 10 squared. Okay, and this is equal to 227.4. Then I will have V at 15, which is equal to A0 plus A1 times 15 plus A2 times 15 squared. And this is equal to 362.78. And finally, V of 20 equal to A0 plus A1 times 20 plus A2 20 squared. And this is equal to 517.35. Okay. Now, this you can just do the calculation. So 10 A1 plus 100 A2, and this is equal to A0 plus 15 A1 plus 225 A2, and this is A0 plus 20 A1 plus 400 A2. Now we are ready. So we need to put the equations in the Gauss elimination. Now this is not easy to solve without the Gauss elimination. From here we start with the Gauss elimination. So here 1, 1, 1, which is the coefficient of A0, 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 then the coefficient of A1. So it will be 10, 15, and 20. And then this is 100. 2, 2, 5, and 400, and this is now the output that we have, which is 227.4, 362.78, 517.35. Okay. Now we will first eliminate these two. So I will subtract row 2 minus row 1, and then row 3. So we will have here row 2 minus row 1, and row 3 minus row 1. Okay, so we will, of course, the first line, nothing happened to it. Okay, 227.4, then this will become 0, 5, 125, 135.74. Now, depends how many significant digits I ask you to watch. You keep this. So this becomes 0, 10, and 300, and this is equal to 290.31. The reason I'm solving this in detail because I think it's a good exercise. And I don't have it solved in the notes so that you can go and practice this. Okay. Now, after we do that, now we go back here. So we have this. Now we have to subtract row 3 minus 2 times row 2. Okay. So this is what I will do here. So it is row 3 minus 2 times row 2. Then what I will have here, this stays as it is. 100, and this is 27.0404. Then this is again, I don't touch 05, 1, 2, I'm done with it. And this is 135.74. Finally, when I do the subtraction of row 3 minus 2 row 2, we'll have 0, 0, 50. And this is 18.83. So I finished the forward elimination. Now I will go for the backward substitution. So here we have 50 A2 equal to 18.83. From this, I can find my A2, which is equal to 18.83 divided by 50, which is equal to 0.3766. And then I will go up, backward substitution. Now I know A2, I need to find A1. So 5 of A1 plus 125 of A2 equal to 135.74. So your A1 is equal to 135.74 minus 125 times A2, which is 0.3766 divided by 5. And from this, you can find A1 is equal to 17.733. And finally, we will have A0. So we have here A0 plus 10 A1 plus 100 A2 equal to 227.04. Now I know A2, I know A1, I need just to find A0. And from this, A0 will equal to 12.05. Excellent. So if I'm done with this, so now my V of t will equal to A0, which is 12.05, plus A1, 17.733 times t, plus A2, which is 0.3766 t squared, and this is defined. You have always to write this 20 and 10. Why? Because this function is only true in this range. It's not true outside the range. Okay? Now from this, you can find your V at, so here I think this is the function. No, okay. I will show it later on. This is V at 16, which is equal to, just substitute, and you will get 392.19 meters per second. From this, I can find the error, the absolute relative approximate error, which is the this answer, which is 392.19 minus the previous estimate 0.7 divided by the current one. Okay, and this times 100. This will give me 0.384%, less than 0.5%. So if you recall, this means that this is good for two significant. Okay, so this is my answer here, and this is the approximate relative error, and this is the function. As you can see here, it's a second order function. It's not a straight line. Okay, and this is the point of interest. These are the 3 points that I used in my interpolation, and you can see here clearly the line is going through all of them, and this is the point of interest that I calculated using this. Okay. Now we can go for cubic. Now I think you got the idea for V of t now. Now in the cubic, I will need 4 points. In the previous one, I had the 10, I have the 15, and the 20. Of course, now the 20.5 will be my point because the other point is 0 from the other side, which is much, and here's the point 16. So this is the 4th closest point to the 16, and you can figure out now that your V of t now is equal to A0 plus A1 of t plus A2 t squared plus A3 t to the power 4. Okay, so I need 4 equations to solve of this. So I need to substitute b of 10, b of 15, b of 20, and b of 22.5. So I will end up having how many equations? I will have 4 equations. Okay, thank you. I like this when someone is correcting me to the spot. This is t to the power 3, not t to the power 4. Okay, it is always the a1 power of 1. Is a2 2 square. A3 t to the power of 3. Okay. Let me see here if you have any further questions. If in the original set of data points there is t equal to 9.75, which is closer to 16 than 22, would you? Yes, of course. I will pick the closest points. I don't have to take from both sides equally. No, I always select the closest point to the point of interest, and this makes sense because it means that the model, if you have a closer point to point of interest, the model will become better and better, and the model will become more correct because you have points closer to the point of interest. Okay, I don't need to solve this now because this becomes too lengthy. Becomes like 4 by 4, and there is no point now to repeat everything here. So you can do that yourself. So here, these are the values. So we have here 4 by 4 system. Hopefully, in the previous example, I reviewed with you how we should approach this problem from the perspective of how to set the equations, how to solve them using the Gauss elimination. Now this will become 4 by 4. Please try it yourself and try to find the value. Now, when you go here, this is my equation now, based on the variables I got in the previous set of notes. This is A0, A1, A2, and A3. Now, one thing interesting you start to notice here. Now, as you start to increase the order of the polynomial, what will happen to the coefficients? Okay, see, this is the linear. This is the second order. This is the third order. You start to have the coefficients of these numbers becomes very small. What does this mean? When you increase the order of the polynomial, their coefficient becomes smaller and smaller. It means that these items or these parts or components of the polynomial, they are not significant actually. Why? When you look here to the data, a linear model would be good actually. Second order, this would be like even better than good. So it means that once you start to see a diminishing factors here, or the components are becoming smaller and smaller, it means that the models that when you try to increase the order of the polynomial, you are not getting much of improvement actually. And you can see here clearly that when you calculate V at 16, it is 392.06. It was 392.19. Okay, and this is good for 3 significant digits. When you take the absolute relative approximate error between this and the previous one, it's good for 3 significant digits. And now, if the function is completely nonlinear, then you will not see such diminishing in the value of t squared and t cubed. So this is a good example. Please try to use it. But very clearly here, you can see a disadvantage of this approach, that first you have to set up a set of equations, and then you have to solve these equations. Now imagine if you have to go for a 5th, 6th, 8th order polynomial, then the system becomes more and more complicated. we want to have a different approach that does not require me to solve simultaneous equation, and that would be the topic of tomorrow's lecture, which is the Newton method. We will solve the same example, and you will find that the Newton method is way better, and you will find the function in one step. There is no need to solve simultaneous equations as we do. But this is for tomorrow. I just want to show you, this is the summary of the results I have. This is the 16 first, second, and third order, and here is the relative error. Now, what I want to show you here is this. I will not solve this example, but I want to demonstrate a fact or an answer and question. Is higher order polynomial always better? Because here in the previous example, as we increase the order, we are getting better and better answers. Okay, we are not overfitting anything, and if you look here, this is even better than the previous example. So this is a real good model. Okay. Now the question is higher order polynomial always better? So let's have this engineering problem, and let's try to see if I fit a second order polynomial to approximate certain value, or if I fit the maximum allowed. There is a term called maximum allowed order polynomial, and you will see that in the practice problems. Okay, so let's understand these concepts. So here it says the geometry of a cam. This is what we call a cam. This is used in engine. So this is more mechanical than electrical. So this cam, if you look here, this is how cam is in the system. So the cam go into a rotational, not very linear rotational function, but it is connected to what we call a follower and attached to a spring through a guide. And when this rotates, this will go only up and down. So you are converting a rotational non-linear motion into a linear motion. So this is the whole idea here. Okay. So this cam, it's a contour. It's not an ellipse. It's not a circle. So it's not easy to find a function for it. And here is its center. This is the center here, and this is how it looks like. So imagine if you want to find a function to represent this. If you want to know what is certain, as in this question here, what is the value of y at certain x? So here the question says, calculate the value of y at x equal to 1.1. So let's see here to the points. I have 7 points, and x is 2.2, 1.2, 8.66. So 1.1 is here, somewhere here. This is 1.1. Okay. So I want to use a second order polynomial to find this value. I will just give you the final answer. I will not solve this, but I'd like to make a point here. And then say the maximum allowed order polynomial. When I use this word, maximum allowed order polynomial, it means that I want to use all the points. Now, how many points I have? I have 1, 2, 3, 4, 5, 6, 7. I have 7 points, so the maximum allowed polynomial is 6th order. So I will have a 6th order polynomial. It means I will have a0 plus a1x plus up till a6, a to the power of 6. So I have, this is the order. While here it's just a0 plus a1x plus a2x squared. The difference that this will be defined. Now for this one, I will do it from 0 to 2.2. Okay, so this one is defined from 0 to 2.2. Sorry, from 0.66 to 2.2. Okay, but this is defined from minus 1.2 to 2.2. So it's defined in the whole range. Okay, so let's see the answer here. So this is defined as from 0.66 to 2.2. Let's go back here. Why I selected this? So the point is 1.1. Okay, so do I select 2.2 or 0? It doesn't matter. Why? Because if you go up here, you add 1.1. If you go down here, it's 1.1. So you can have the model either defined from 0 to 1.28 or from 0.66 to 2.2. So both are the same. Okay, so my model here is defined, selected to be between 0.66 and 2.2. Okay, now when you look to this, this is defined only in this area. When you look to the shape, okay, not bad. It's sort of following the curvature. Okay, it's relatively okay. And if you want to find your y at x equal to 1.1, okay, 1.1 will be something like this here. So I will go up here, and this will be my value, which looked reasonable for me because the curvature is really looks. I don't know the error exactly. That's not my point, but the point here is it looks okay for me. Now let's see what will happen if I go for a sixth order polynomial. And this is the sixth order polynomial I told you about. This is for 6, defined for the whole range from minus 1.1 to 2.2. Look to this. Of course, that's definitely completely not true, not correct. Does not really represent. When you go to 1.1 here and try to find the 1.1 values, so here it becomes looks to me that's way off. And even the curvature, you can see here that this does not really look like this curvature. It doesn't look like this curvature. Okay, so here is the advantage here that so it is clear that having higher order polynomial is not necessary that this will lead to a better answer. Okay, so sometimes 2, 3 order second, third, that's it, defined with certain limits. That is much better than defining something that goes through the whole range, especially when the function is different. Because here the difference here, when you look here to this curve, the function is different. This function, for example, here is different than there. It's not the same function that can define, for example, something like here or something like this or something like this. So if you want to find a function that fits all of them, then this will be a clear example of overfitting. Okay? So it's better to have segments of this whole function and find the suitable function for each one. Okay? So I hope that with this example it's clear for us what is interpolation, why we use it, and what are the limitations. Now we understand the technique that we use has one disadvantage, because we have first to solve, to substitute, then we need to go to another problem, which is solving another set of linear equations. If we want to avoid this, if we want to find a better way, that will be our next topic, which is the use of Newton's method.